Let us start by defining the notion of a polynomial system. A polynomial system is by definition a collection of one or more simultaneous polynomial equations in one or more variables. For example, a typical one-variable polynomial equation, such as x squared plus 2x minus 3 equals 0, so that would be a polynomial system. Of course, a polynomial system consisting of only one equation with only one variable. The variable is x. Typical polynomial systems would have more than one variable and more than one equation. Here is an example. The first equation is y squared plus xy minus 4y minus 2x plus 4 equals 0. And the second equation is y squared x minus 2y x minus y minus 2x plus 4 equals 0. Notice that when we write polynomial systems, it is usually custom to write a vertical line next to the two equations. So this vertical line indicates that the two equations are taken simultaneously together. So that indicates the fact that we're speaking of a polynomial system. Okay, so we said that this polynomial system has more than one variable and more than one equation. How many variables do you see and how many equations do you see? Well, I'm sure you saw two equations and you hopefully saw also two variables, namely the variables x and y. The number of variables in equations need not be equal. For example, we could have the following system: x plus y plus z plus w equals 2, y plus z squared equals 1, and y plus zw squared equals 1. This system would have 4 variables, I'm sure you guessed it correctly, but it only has 3 equations. So the variables would be x, y, z, and w, and the equations are only 3. So it is possible to have that the number of variables is different from the number of equations. It is also possible to have it the other way around. It is possible to have more equations than we have variables. Polynomial systems may fail to have solutions. For example, let's look at this system. The system of two polynomial equations. The first one is x equals 0, and the second polynomial equation is x times y equals 1. Now the first equation clearly implies that x is equal to 0, but then the left hand side of the second equation is 0 times y, and 0 times y is always equal to 0. So no matter what we choose for y, we can never satisfy the second equation. So the second equation will never be solved. So that polynomial system would fail to have any solutions. Polynomial systems may have finitely many solutions. For example, here's a system with only one solution: x equals 0 and y plus x equals 1. Let's check that that system has only one solution. The first equation again implies that x is equal to 0. The first equation simply says that x is equal to 0. And then in the second equation, if you were to replace x with 0, we get y equals 1. So that is a polynomial system with only one solution. Polynomial systems may have infinitely many solutions. For example, let's take a look at this one. X equals 0 is the first equation, and the second equation is y plus z equals 1. If we set x equal to 0 and y equal to 1 minus z, we produce infinitely many solutions for every possible value of z. So if you were to set y equal to 1 minus z, if I replace y with 1 minus z, z cancels, and I always satisfy the equation y plus z equals 1. So this would be a system that has infinitely many solutions. For every value of z, I can produce one value of x, namely the value x equals 0, and when one value of y, namely y equals 1 minus z, which solves my system. The branch of mathematics that studies exact solutions of polynomial systems is called algebraic geometry. Now, algebraic geometry is a very wide branch of mathematics, and the practical aspects of solving polynomial systems are covered under a relatively small sub-branch of algebraic geometry. That is called the subject of elimination theory. So how to practically solve a polynomial systems, that is subject of elimination theory. Solving polynomial systems is an indispensable mathematical tool which can be used in other branches of mathematics as well as directly in the other sciences. There are also some direct applications of polynomial systems. For example, the equations of kinematics. Think of the possible configurations of a robotic arm. So, possible configurations of a robotic arm, those are directly described by a system of polynomial equations. Whether a polynomial system has finitely or infinitely many solutions, what are these solutions? All of these things can be computed with a computer algorithm. In fact, the algorithm can roughly be summarized like this. Find something called a Grobner basis, named after the Austrian mathematician Wolfgang Grobner. Actually, you do that using the Buchberger algorithm. That algorithm is named after the Austrian mathematician Bruno Buchberger, that he was a student of Grobner. And then use the so obtained Grobner basis and techniques from the subject of elimination theory to explicitly find the solutions of your polynomial system. Now, these algorithms are way too advanced to cover here. In fact, the algorithms that I just described would be a specialized course in university, usually studied by math majors. Something more, these computer algorithms for solving polynomial systems are not well suited for pen and paper computations. Such computations can get notoriously large and may even require supercomputers. However, a polynomial system which can be solved by hand would typically be solved in milliseconds on a modern computer. So yes, we can have big problems with the practical aspects of solving polynomial systems, but whenever we have a polynomial system which is difficult on a computer, that polynomial system would usually be intractable by hand. So we would have no idea how to do that by hand. A system doable by hand would typically not require these advanced algorithms. A polynomial system which you can solve by hand would typically be solved easily using ad hoc techniques. That is why, in the remainder of this lecture, we're going to cover such ad hoc techniques. So we will not focus on some general algorithms for which we need computer, because such general algorithms will not be used or expected to be used on a typical math exam.